All right, so last section of chapter 2 is 2.7, related rates. Basically, just to give you an idea of what we're going to be solving or what we're going to be looking at, it's going to be good if you're a decent drawer. All right, so drawing pictures to kind of visualize what's happening. So let's just say, I'm going to try my best to draw at the balloon here. So let's say we've got a balloon and air is leaking out. Okay, try to make it. Let's say this is a spherical balloon. So the shape is going to be important. But what we're going to use calculus to solve for is, say air is leaking out at a certain rate, so a certain speed, right? Rate and speed are synonymous. All right. And so we might say the rate of change of the volume is -2 cubic inches per minute. And it would be negative, so we'll need to understand when rates are positive and rates are negative. It would be negative. Why, in terms of this problem, why do you think we would say that the rate of change of the volume is negative? It's coming out. So the volume in there is becoming smaller. When it's increasing, it will be a positive. And then what we're going to need to do is we're going to say our question is find the rate of change of the radius. So if we look at the radius in here, the radius of the balloon, so imagine a balloon, your air is coming out of it. Usually happens pretty fast, right? You can pop it. But what's going to happen to the radius? So and look, I want you to understand what we're measuring. We're measuring speeds. How fast is this changing as opposed to how fast that's changing, right? That's what we're going to find. So we're going to find that speed. So first of all, it's more of a velocity, right? Because we're putting a sign. You learn in science class that speed has no sign. Velocity, you put positive or negative. So what's going to happen to our radius? Increasing or decreasing? Decreasing, so that answer would need to be negative. But we're going to use calculus to find those. So now what are some, so this is the pose of the problem. This problem we will solve today, okay, hopefully. If I do my job right, we'll get to this. So, lost my train of thought. Reverse the situation. Who all in here has pumped up a balloon before? With blowing air into it, right? You blow air in, I should have brought a balloon. You blow air at the start, you can see it's expanding, expanding, expanding. But think, your lungs can only blow so much air in at a certain rate. And as that balloon gets bigger, think about when you're blowing the air in. Do you see as rapid a change as you did at the start? It slows down. How fast it's expanding slows down because now you got more volume to fill. Okay? So we're going to see how those speeds compare. At this moment, if the air is going in this fast, how fast is the radius changing? Another situation that I remember as a kid, all right, that sticks out to me that now we can use calculus to compare. Who else filled up a bathtub before? All right, or watched a swimming pool fill up. That's really miserable. So here, this the speed at which this water comes out, that's a rate. That's we're going to look at, and that adds to your volume. Okay, and think about it. So the water goes in the bathtub, but this height of the water in there, does it rise very fast normally, or does it rise very slow? Very slow, and we'll see exactly how slow it is. We will be able to use calculus to compare the rate of change of how fast the volume is being added to how fast the water level rises. Obviously, it depends on how much room is in here, right? Because that water has to disperse. Okay? So those are the two, I call this the bathtub problem. This is the bathtub, and maybe the balloon problem. Maybe not do the bathtub problem today, but we'll for sure do the balloon. we may look at it at both ways. Maybe air could go in or air could come out, and how could that affect the balloon, okay? So I'm gonna erase this, we'll just leave it there for a second. You know, you can pause and kind of draw those pictures. You don't have to be the best artist, but it helps to visualize. Drawing is gonna be an important aspect of solving math and science word problems, okay? It's something that we do. All right, so real quick, there's some things I wanna review. The first thing I wanna do at this point, because we're done with new calculus rules, is I wanna do two things. I wanna review all of our derivative rules, and then I want to also review some basic geometry formulas. And you can see there that we had a sphere. And spheres have, what are things that we use to measure with a sphere? What could we measure? More specific, think larger. But yeah, radius, diameter, we would need those then to calculate what might be something in the entirety we might calculate. Surface area, so that outside part, the volume. Yeah, so think area and volume formulas. So we're gonna need to know those in order to work that. All right, so let's go through our derivative rules. I'm just gonna write these out. I'll put them here. If you don't wanna write them all right now, you don't have to because they're gonna be stored. All right, but, so we'll start off our basic power rule. U to the n is n times u to the n minus 1 times u prime. Our trig rules. So I'm going to call it out, you tell me. Derivative of sine u times u prime. All right. Derivative of cosine u. Negative sine u times u prime. So this is a game. You have 3 seconds to give the answer. Derivative of tangent u. Secant squared u times u prime. If you don't know it in 3 seconds, you don't know it. So we got to know it better, right? This is how you do it. You get in the habit of writing them out. Here's how I remember this one. If I know tangent, then I know cotangent. I put a negative in front and a co. So negative cosecant squared u times u prime. All right. Secant u. Excellent. Secant u times tangent u times u prime. And if you know that one, Ivan, then you know cosecant u. All you got to do, again, same relationship, put a negative in front. So what would it be? That's exactly right. And on all of these, we're doing u prime because u is a what? Function of x. Very good. All right. Now we have the transcendental functions, those e's and ln's and logs. So we're gonna just, and I'm not putting your product and quotient rule because those are more, these are just for functions. Okay. E to the u, what's that one? Times u prime, e to the u times u prime. A to the u was one that we added that's very similar to e to the u. So I will put it right next to it. Do you remember what a to the u is? It's a to the u times u prime times ln of a. So that ln of a is a constant. Okay. Derivative of ln of u is u prime over u. Sorry, should have given you a chance there. Then, but the reason I wanted to put that is now I can do log base a of u, and I do change of base. So do you remember what this one was after the change of base? So you're going to get a 1 over ln of a in front, and then you'll have ln of u, and the derivative of ln of u is u prime over u. So you got to do change of base in there. All right. Which ones am I lacking?
the inverse.
Yeah, the 6 inverse trig. Now I'm going to put them in pairs like this. So I'll put arc sine of u and arc cosine of u next to each other. Because if you remember, those are very similar. Do you remember this one, arc sine of u? U prime over square root of 1 minus u squared, and arc cosine of u is negative u prime over square root of 1 minus u squared. All right? Arc tangent of u. Remember that one?
U prime over 1 plus u squared?
Yep. Arc cotangent of u. Yeah, same as arc tangent. The reason I'm putting these over here, all I gotta do is put a negative in front. Then the last one, you don't use this one as much, but you need to have it. Arc secant of u. U prime over absolute value of u times square root of u squared minus 1. That's right. And then arc cosecant
negative u prime over absolute value of mu times square root u squared minus 1.
All right. And that, at this point, are all the derivative rules. They're all in one spot. I highly encourage you to put them all on one page. Okay? Because that way you have them all in one place. You can go and refer to them. Now you can add your product and quotient rule to this. Those I'm not worried about. I figure you're pretty solid with that. Derivative of a constant is what? Oh, we could add a couple. We could add, what about derivative? I'll put it right over here. I guess the geometry formulas, they got overran. So derivative of square root of u, what's that? You remember we made a formula for that.
1 over 2 square root,
Right. U prime over 2 square root of u, very good. Any other ones? The derivative of a constant is always what?
0.
0. Can't think of anything else. Those are all the rules you would use in differential calculus. Now, of course, you've got chain rules and product rules, and all that, but that's them. 1, 2, so 6, 7, 8, 9, 10, 11, 17, 18, 19, yeah, about 19, 20 rules. And in my opinion, this is the easy part of calculus. There's two types of calculus. There's differential calculus. There's more than 2 types, but 2 general. Differential calculus and anti-differential calculus, or integration, which is working backwards. Here's your derivative. What did you take the derivative of? So the whole, yeah. And then there's a whole new crop of rules that we will end up using. And then we should end up having about a lot. I mean, maybe around 19 or 20. Okay, so it's here. It's in the video. You can pause it, write them down. All of those rules are there. We're gonna start erasing. I'm gonna erase over here. I'm gonna start putting some basic geometry rules. Okay, so I'm gonna erase this column here. And I want to put some, like not more formulas, right? Just some formulas, so some geometry here. Yeah?
What does it say for the denominator on the
Absolute value of u, square root of u squared minus 1. All right, so a sphere. So the volume of a sphere is always 4/3 pi r cubed, and the surface area is 4 pi r squared, okay? So I thought that would be helpful to have that, okay? This is for a sphere. I'm gonna do a sphere, a cylinder, and a cone. Volume of a cone, I'm sorry, a cylinder is pi r squared h. That's all I'm going to do for now. The surface area is a bit of a pain. I mean, lateral surface area is 2 pi r times h. You can think about where that came from. And the surface area of the top or bottom, it's just pi r squared. It's the area of a circle. Okay. All right, I'm going to erase this set now. Okay, I'm running out of room. All right, what about the last 3D one we'll do is a cone. All right. Anybody know the volume of a cone? 1/3 pi r squared h. So if you can remember that a cylinder is pi r squared h, you can remember a cone. It's 1/3 pi r squared h. All right. Then a couple of 2D. How about just a circle? We'll look at some 2D. So there's our radius, our area of a circle is what? Pi r squared. Our circumference of a circle is what? 2 pi r. All right. Last one, triangle. The area of a triangle is what? Yeah, 1/2 base times height. And then you've got the Pythagorean theorem if you want to write it like this. A, B, and C. This is for a right triangle. A squared plus B squared is C squared. I think that's pretty good there on a geometry review, all in one place. That would be helpful. So it's kind of crazy that I'm referring to all this before we even do the lesson. But I wanted to summarize all of your derivative rules. So you have all your derivative rules in one spot. And you have your some basic geometry formulas in one spot. Lateral surface area of a cylinder is an easy one to show you. Lateral, so a cylinder. So would you guys, well, take this little magazine thing. If I took this magazine, right, and I just do this with it, try to connect it perfectly there. Trying to show you there. So here we go. That's a cylinder, right? This is a circle at the end. So what's the surface area here? Well, the lateral surface area of a cylinder is just the distance around here times the height because it's a rectangle. 2 pi r is the distance around the circle, height is the height of the cylinder, see? It's a rectangle. We want to know this area. Watch again, it's magic. Here's your cylinder, right? We want to know the lateral surface area, not the area of the top and bottom. Those are circles. Well, it's supposed to be a circle, right? So we want to know this area. Again, if I unravel it, this distance is the circumference, right? So there's 2 pi r, and that's your h. Okay. All right, this will be in the video. You can come back to it and write it down whenever, okay? And I'm gonna start erasing the left-hand side again. All right, we'll leave the right-hand side for you. Okay. So, what are we being asked to do? All right, let's just. All right, let's say we have the equation. We'll just get started, example 1. Let's say we have x squared plus y squared equals to 4. We've given this equation. What's that the equation of? A circle, all right? Can I finish erasing? It's in the it'll be in the video, guys, so I'll email this. It may take me a little bit today because, you know, this is a rat race today. It's boom, 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 boom. And we got a lot of classes in a row. All right, so don't have to really know the shape of this to get started, but I think you do know. All right, it's a circle. Here's what I want to talk about is if we want to maybe look at how things are related, right? Maybe this circle is moving somehow. Maybe it's growing, or maybe it's shrinking, or something like that. So maybe we look at this point here, and maybe we know that that this point is moving this way and this way, and so the whole circle's kind of expanding or whatever. But the point I want to make is that when we're looking at speeds, when we're looking at how fast something moves, how do you calculate a speed? When you calculate a rate, how do you calculate a rate? You're thinking, you're right about that. In terms of the math, that if we're looking at a function, then you're exactly right. We would use slope, but I'm being more like if I was in a car. Yeah, just distance over time, right? So just to simplify that, because I want you to kind of see that you're right, because look, it is distance divided by time. That's and what Eli says is exactly right. We're going to do change in distance, or either instantaneous change or average change, which then connects to the slope. And look, we have your fraction here, Elijah, that you were, because if you're doing slope. So, but just to generalize it, it's a change in distance over a change in time. Everybody with us on that? Okay, we got that. So change delta D over delta T. Okay. That's how we calculate rates. And if we run the rate at an instant, so we want an instantaneous rate of change, it wouldn't be delta, it would be what? Yeah, but what do I use to get instantaneous rate of change? What's the connection? Yes. It would be the derivative of the distance over the derivative of time, right? That's over like an average if we're doing an average speed. This is more of secant line, this is more. So look, I want you guys to understand that when we use the terminology instantaneous rate of change, we got to automatically use derivative, because Elijah connected slope of tangent line and Eli connected the real world change in distance over change in time. Okay, so my point is, if we're looking at some point on a circle moving, okay, and it's moving in a certain speed, the point on the circle is not a function of y. See, the x and y on that circle are both functions of time. Because, right, think about it, as, what do we look at? We look at, think about when we normally take derivative, what is it? It's dy over dx, right? This is the rate, this would be the rate of change of y with respect to x, or a function of x. So that's what we've been doing. But now that we get into real world and we're looking at speed, we usually everything's related back to time when we do speeds. So let me say it again. X and y are functions of t. All right? So here's what we're going to be asked to do. Find the rate of change of y when x is 1 and dx over dt is 2. All right, so let's talk about this. All right, so this is a kind of like the intro into kind of how are we going to work these related rates problems. All right. So the first thing I want you to see is this. So before we start working the problem, we look at this. Where did you see problems like this before? X squared plus y squared is 4, and we had to do derivatives. Where did you see those? Yeah, but in this class. Yes, that's an implicit. Notice that here we don't have solve for x or y. So when we did these implicit, we did derivative with respect to what? When we went through, back in 2.5. With respect to x. And we said, if the variables don't match up, you got to use what rule? Remember, if we said if this is a y and that's an x, and the variables don't match up, you got to use what? Chain rule. And we went and did the derivative with respect to x because we said y was a function of x. Okay? But now, notice what, and we could have went through, we said 2x plus 2y times dy over dx, or y prime equals 0. And then we would have went from there, and we would have solved. Okay? That's what we did in 2.5. Here's what's different. You're not going to take the derivative with respect to x. You got to take the derivative with respect to what? Time. D over dt. So x is a function of time, and y is a function of time. So we're going to take the derivative with respect to time, and it's got to be implicitly because there's no t in it up here. So everything has to be done implicitly. So you're going to do the same methodology you did in 2.5, except you need to put a different symbol at the end when you do your chain rule. It can't be something over dx because there's no dx now. So see if you can take that derivative with respect to time and you'll see what we get. All right, so let's look at and see if our derivative formula makes sense. Okay, or our equation. So how do you take the derivative of x squared? You just do what? Yeah, so what do you get? 2x. But now, notice you've got to apply chain rule because this is a function of time. It's like if I had this, x is 3t, right? If I had this equation, x is 3t, I would have to say the derivative of both sides with respect to t. Derivative of 3t with respect to t. So that's the idea, okay? So x is some function of time. There's some formula with time. That's how x is moving. All right, so it is 2x, but I have to apply chain rule. So I got to do, so the 2 goes down in front, right? Then I got to do the derivative of the inside with respect to time. There's your dx over dt. There's a rate. That represents how fast x is moving. How fast we're moving in the x direction. Okay? So that's a rate. Then plus, what's the derivative of y squared with respect to time?
2y times py over.
Yeah, did you just put x prime and y prime? Did anybody put x prime and y prime at the end? It's fine, but I like to put it like this so I can see it's a speed. From what we talked about earlier with Elijah and Eli. We were talking about the distance over time. Here, see, x and y are distances, see? And there's your time. All right? And then what's the derivative of a constant? 0. So what you have now, and this is a rate, see? So let's be specific. This is the rate of change of what with respect to time? The rate of change of x, very good. This is the rate of change of y with respect to time. So basically, you got a point that's moving around the circle. So that this point is moving, and as it moves, it has a speed in the x direction and it has a speed in the y direction. So notice, look at this point. If dx over dt is positive, that means its speed is that way. That means the point's going this direction. So if the point's going in this direction at 1, what's happening to the y? Is y going up or y going down? So we should see that in our answer. Okay? So, all right, so how could you simplify this formula real quick? Is there anything you could do? Yeah, divide everything by 2, right? You divide everything by 2, here's what we get. X times dx over dt plus y times dy over dt equals 0. All right. So what you're going to be doing a lot of is you're going to get an equation with these speeds in it. So this is how these speeds are related. If this is how fast we're moving in the x direction, then we're going to be able to find out how fast we're moving in the y direction. We just need a location. Because your location on the circle depends. Because here, if I'm moving right, dy over dt is going down. It's decreasing, it's negative. But if I was going left, dy over dt should increase. Right at this spot, right here at 1. So notice I gave you some information. When x is 1 and dx over dt, I could be like 2 inches per second. It should be what am I looking for? A unit there, and we will get those. Okay. So now all we're going to do is once we get our equation with our speeds in it, we're going to sub everything in. We know x is 1. We know dx over dt is 2. We need to solve for dy over dt, but I know y. I don't need the problem to tell me why. I know the y variable. I know what it is. So if I go back to this, look up here, guys. If I go back to this, okay, I can find y if I plug in an x. So right here, if I plug my x in, I can find y. So if I plug x in, 1 squared is y squared. I'm sorry, 1 squared plus y squared is 4. So I get y squared equals 3. Do you agree with that? So y is either plus or minus the square root of 3. All right, because I want to show you both situations when it's going to come out positive, when it's going to come out negative. So either we're looking at this point, 1 square root of 3, or we're looking at this point. So the first thing I want you to understand is when I see that dx over dt is 2, that means the way the point is moving is that it's going in this direction where the x should change by 2 in a second, 2 inches in a second. So I know that it's moving right. So if I use this for y, as the point moves this way, because it has to go along this circle, then my y should be negative. So let's see. So I'm going to plug this point in. So I'm going to use square root of 3. And now I'm going to solve for that. So I have 2 plus square root of 3 times dy over dt is 0. And I get dy over dt equals negative 2 over square root of 3. I get a negative because it's going down. So my answer, my negative speed, my negative rate should correlate to what's happening. Because as this point moves right, y is decreasing. If I was down here though, this isn't 1 square root of 3, this is 1 what? Not square root of 3, negative square root of 3. And if I'm over here and my point is moving this way along the circle, right? So it's got so as the point's moving, what we're saying is, as the point's moving around the circle, it's got a speed, a horizontal speed and a vertical, like as you're tracking it, it's going in the horizontal direction, it's going in the vertical direction at a certain speed. Well, notice what's happening to my y over here. My y is what? Increasing, so it should come out positive. So if I put that point in, 1 times 2 plus negative square root of 3 times dy over dt. Then when you move this 2 over, you get negative square root of 3 dy over dt is negative 2. You get dy over dt is 2 over square root of 3. Positive. Oh, crap. Barely. Forget it. Okay, so let's just rewind. You have an equation. You will be taking derivatives implicitly, but not with respect to x. We took our derivative with respect to t. And we use implicit differentiation to come up with this. And this, we call it, this is the equation that relates speeds or rates. So look, I should use the word rate. I know rate's fancy, but it is rates. So look at this, here's my point, right? Watch my hand. If I go like this, around, the point moves around, it's got, so like right when I'm here, what would you say if I'm going this way? What would you say dx over dt is? Right here. But when I get here, you're just going to give me positive or negative. What's dy over dt? Yes, because it's going left, which that's negative in the x direction, it's going down. Dx, dy. Very good. And that's the introduction to related rates. That's just the tip of the iceberg. I actually think the other problems are easier. Hmm? All right, a lot going on there. So what skills have we tied in? Do we need to remember implicit differentiation? Yes. Do we need to maybe remember here, just, I have to still go in and solve for y. And here's just solving an equation. Once I plugged everything in, I was able to solve the equation, okay? But implicit derivatives are going to be big. I'm running low on time, so I want to at least mention this problem. So let's go back to our balloon problem real quick, okay? This is in the video. Don't worry, 2.7 is not going to be due till later next week. I mean, I'll open it, but I haven't even, and we're looking like Wednesday or Thursday. It's going to take us several days, so don't worry about that. So, our balloon problem, right? Spherical balloon, and it's got a leak. All right, and we know that the rate of change of the volume is -2 cubic feet per minute. Find the rate of change of the radius when the radius is 1 foot. Okay. All right. So now we are in, this is our example 2. Now we're more in to our word problem. Okay. So there's a leak in the balloon. You're assuming the balloon is pumped up. All right. So, a couple of things. I need to know the figure and I need to know are we looking at, more of the volume or more of the area. So our figure is what type of shape, and we're referring more to volume or area. Volume. So I'm going to go ahead and write out the volume of a sphere. So what's the volume of a sphere? Pi r2. Yes. Now let's see if you agree with this. Look at here's my balloon. Imagine my balloon right here. I got my balloon. I'll put my hands here. There's my balloon. Okay? I got my balloon. Air is leaking out. So what's happening to the balloon? The balloon is what? Shrinking. So as it shrinks, its volume and its radius are functions of what? Time. Because as time increases, what happens to the volume? It decreases. What happens to the radius? So volume and radius, it makes sense here. V and R are functions of time. So anytime I want to relate rates, if I want to relate those speeds, because that's what this is. Tell me the mathematical formula for this, rate of change of volume. What symbol, what math symbol is that? Rate of change of volume. This is where you have to go from dV over dt. It's got to be with respect to time. That is the mathematical symbol for rate of change of volume. What's the rate of change of radius? dr over dt. Does everybody see why we're putting dt? Because it's a speed. Okay? All right. So now we go to our equation. Not very pleasant looking, but v and r are both functions of time. So I'm going to take the derivative of the left with respect to time, and I'm going to take the derivative of the right with respect to time. Now, don't freak out when you see all this 4/3 pi stuff. I know I'm running low on time. Guess what the derivative of volume with respect to time is? You don't do anything. That's it. dV over dt. Now over here, 4/3 pi is a what? Constant. So I'm going to bring it out. Now, how would you normally do the derivative of r cubed? Yeah, well, you would get what? 3r squared. But now you got to do chain rule. You got to multiply by the derivative of the inside with respect to time. Otherwise, I won't get my rates. And this is how the speed of the volume and the speed of the radius are related. It's miserable looking, but that's it. So now, what little math could you do real quick? What could you cancel? Threes. It would be v over dt. It's 4 pi r squared dr over dt. Just plug and crank. Rate of change of volume is -2. Rate of change of radius is 1. I sub those in. If I divide by this, I get dr over dt. Due to time constraints, we move forward in this lesson. It's going to be feet per second, right? I would say feet per minute. Dr over dt. Now, so if I divide by 4, because 1 squared is 1. If I divide by 4 pi, that's going to cancel. Make it 1 over 2 pi, right? 1 over 2 pi. Does it make sense that it's negative? Yes. And that's like 1/6. See, think about how that slow movement there. Remember when we were talking about looking at a balloon blow up, or maybe it's so you can see how fast that the radius is changing. It's -1/6 feet per minute. Okay. All right. I'm going to stop there. This is just intro to related rates.